I3, center of mass for a rod of length L. Now, the usual way to do this is with calculus, but what I would like to do for you is to show you how to do it without calculus first. In fact, I'd like to do this more than one way. Remember that in physics and engineering and in life in general, it's always good to know more than one way to do something, all right? And I apply that in my everyday life. For example, if I'm going to get to school, I can drive, but I could also bum a ride off a neighbor. My wife could take me. I could take the bus. I could walk. I actually walked home a couple times from school. And also I could take a taxi or Uber, which I never really had to do because I had the other ways. So it's good to just have backup plans and other ways of doing things. So if you haven't gotten as far as these integrals that we need for calculus, I'm going to set you up and review some calculus for you. First way I'm going to do this, and remember doing things more than one way, is it's inspired by Feynman, who once said something to the effect that any good physicist has 6 or 7 ways to understand, a given concept or result. So let's try here method 1 in finding the center of mass of a rod, and I'm going to call this the symmetry method, or using symmetry. So we have a rod here, and this is going to be, we're going to do it from respect to the edge here. So put it at the edge, and we're going to find that the center of mass by putting the origin at the left will help us apply some of the things more easily that we did earlier. So I'm going to divide this up into sections like this. And here we can pair them off. Like this one can be paired with this one. This one can be paired with that one. That one there can be paired with this one. And say that one, check mark there, a dot there, a dot there, and say a slash there, slash there. And in the notes, I went ahead and made these in color. So if the length here of the rod is L, we know when we have 2 masses that, if you take this block and this block, that the center of mass for those would be in the center here. But see, this block and that block has the same center. And then the next pair, same center. So that means since all the mass pairs have the center of mass in the center of mass is going to be in the center. If I say L over 2, then you can look at that center of mass as being in the center of the rod and forget where the origin is, doesn't matter. Later, when we do moments of inertia, it will matter, where the reference is, where your axis is when you're doing rotation. But for the center of mass here, which is the center of the rod, and we're finished. Now the second method, I mentioned this in the earlier section, the balance point. That the center of mass can be thought of as the balance point, and that's assuming that the rod has the same density everywhere. That's uniform density, and that gravity underneath the rod is the same everywhere, like 9.8 meters per second squared, say, for a local region on the Earth. So if that's the case, where do you put, say, fulcrum to balance the rod? And it would be the center. So the balance point is the center. And that's another way to find the center of mass. Here's a cute little toy, has a bird that looks like has more mass back there, and it's like floating, but really these front parts, these wings, stick out very, very much this way, and they are massive, so that when you balance it, it kind of looks like an illusion, like it's not balanced, but really it is. Method 3, I'm going to sum small masses. Now this is the idea of calculus, but we're not going to use calculus. We're just going to do it by summing. So here, if we have the various blocks broken down, this is x equal to 0 here as our reference, and then this is going to be length L and also mass capital M. Then each of these will have a small mass, which we're going to call, delta M, as the big mass over N, where N is the number of the number of small blocks. And then the delta X that goes with this would be the big L over N. So if you multiply L times delta X, you would get then the entire length. And if you multiply N times delta M, you would get the total mass, like that. So the center of the first one here is going to be delta X over 2. So that's going to be where we can consider the first distance in our formula that we're going to be applying. We need to have the distances to all the masses. Then this one here would be 1, 2, 3 halves delta X. And then this one would be a half, it's 2, 3, 4, 5. This would be 5 halves delta X. And then if you go to N, this one, we basically want the nth odd number. You can think of this as 1 delta X over 2. It's 1. This one's 3. So see, X2 has the 3. And then the third case, X3 has the 5. So that means the nth case is going to be a delta X over 2, but I need here the nth. This has to be the nth odd number. So we can think about that like this. If we have N is 1, 2, 3, 4, like that, then the odd, the nth odd number, this would be 1. The second odd number is 3. And the third odd number is 5. You had the odd numbers, 1, 3, 5, 7, like that. And this would be 7. And then what would the nth one be? Well, the nth one would be, let's see, this is, if you take 2 times 2 and subtract 1, you get this. If you take 2 times 3 and subtract 1, you get the 5. If you take 2 times 4, you get 8, subtract 1, you get the 7. So 2n minus 1 is what you're going to need in here. 2n minus 1. So now we have all the little m's and the little distances. So when you use the formula XCM, you need to have CM1 x1 plus m2 x2 plus m3 x3 plus ... mn xn, and then you're going to add up m1 m2 m3 mn. So that's the formula. Now, the neat thing is that all the m's are going to be delta m because they're all the same. So all these are, you know, delta m's. And then the x's, I can replace here. I have a 1 delta x over 2, and then a 3 over 2 delta x, and etc. So if we do that, so let's do that. x1 is delta x over 2. x2 is 3 delta x over 2. And then the third x is 5 delta x over 2. And then the last one here would be 2n minus 1 delta x over 2. So if we do this, we're going to have xcm. Now, delta m is going to be everywhere here because all the little m's are delta m. So we're going to have 1 plus 3 plus 5 plus dot, dot, dot. I'm factoring out the delta x over 2 at the far right. And this is going to be 2n minus 1, and then delta x over 2. And then we're going to divide by all the masses. So here, delta m plus delta m plus delta m, if you add up all the masses, you're going to get the total mass, m. So this is the relation. All the x's here have delta x over 2, so I put that out here. And then we have the odd numbers, 1, 3, 5, 1, 3, 5. And then we have delta m everywhere, so we pulled that out like that. So there's our formula so far. But remember that the delta m is capital M divided by n. So that means if we had delta m divided by big M, like we have here, we would just have 1 over n. So that's kind of neat that we can do that. In other words, by replacing this with capital M over n, that may be the easier way of looking at it, then the big M's are going to cancel out, and you're going to have the formula, the center of mass, is going to be 1 over n, 1 plus 3 plus 5, dot, 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 2n minus 1 times delta x over 2. Now, what is the formula for solving, let's say, the problem of adding the first few, and in general, n odd numbers? Because remember, we have here n odd numbers. And there is a very, very cute way of seeing this, that if you have a square and divide it into pieces like this, all the squares, smaller squares are the same. This is 1. If you go here, if you add, for example, these 3, so the first, so you put a 3 there, and a 5 and a 7, watch this trick. If you just add the first odd number, you have 1. If you want to add 1 to the 3, then you have 4, which is, this is 2 by 2. If you want the third odd number for the 5, well, if you have 1 and you add the 3, then you add 1, 2, 3, 4, 5, you get 3 times 3. So you could do this, work this out, that if you have 1 and then 1 plus 3 you get 4. And then 1 plus 3 plus 5, that's going to be 1, 3, that's the 4, and then 1, 2, 3, 4, 5, that's going to be 9. And then 1 plus 3 plus 5 plus 7, which you can see here, if you 1, 2, 3, 4, 5, 6, 7, you then get the 4 by 4. Should be 16. That's check. 4 plus 5 is the 9. If you add the 7 to the 9, you get 16. So see, this is the nth case, and you're finding here, this is going to be n squared, the formula. So if the second case, this is n is 1, n is 2, n is 3, n is 4, you get these results. This is kind of neat. There's a picture in the book with some color showing a visual proof of this relation. So let's just look at this a little more carefully. If you have n for the nth case, 1, 2, 3, 4, and say n, and here you're going to have the nth, n odd numbers. So here you get a 4, and then 4 plus 5 is 9, and then 9 plus 7 is 16. So all you're doing here is you're squaring the n. That's 1 squared. Say this is 2 squared. This is 3 squared. This is 4 squared. First case is 1 squared. So that means the nth case will be n squared. So looking at that, so here we have n odd numbers. So we add those up, that's going to be n squared. So the center of mass is going to be 1 over n times n squared times delta x over 2. Now one of the n's going to cancel. You're going to have n delta x over 2. But what's n times delta x? That's the length. So we did it. The center of mass, it's in the center of the rod, and we didn't use any calculus. Okay, now the fourth case, method 4. The fourth case is going to be using calculus. So you have the rod, length L, and here's our origin we're going to pick. So we come out here a certain distance x to some arbitrary place where you have here a little dm, a differential, a little bit of mass. Total mass here is big M as before. So the x center of mass is going to be 1 over m, and we're going to sum up here the m and the x is like this. From I goes from 1 to n. This is nothing more than a summation notation where the I has to become all these from 1 to n. So you would have dot, 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 and then mn, xn, and then you would divide by the capital M. So this is our formula, setting it up with a sum. Now to go to calculus, what you do here is, in fact, you would probably just set it up the way I'm going to write it down. You'd have 1 over m. You have an integral from 0 to L of x with the little dm. So you would start here with this calculus form. And here we can write the dm, the little piece of mass, is going to be equal to big M over L times dx. In other words, we're doing a proportion. That the mass for this little delta x, you would compare the delta x with the total L, and that would have to be the delta M over here, the total mass. And you could also write that as deltas and then take the limit, But anyway, what we would do in calculus is we would just, well, probably in calculus, I would say the dm is some density times dx, and the density function, since it's constant, is m over L. That's how I would arrive at this equation. I think that you would normally just say the little piece of mass is proportional to the little distance or thickness, and the proportionality constant's lambda, the density, linear density, and that's big M over L. So when we do that, we have 1 over m. And here, one might argue you shouldn't integrate this to L because you don't have a dx there yet. You have an m, so you might want to say the dm, in other words, this variable limits should correspond to the differential, so from 0 to m. But here we go right to this. We would have 0 to L. We would have lambda x dx, so the dm is lambda dx, so lambda dx, there's your dm, and your x is there. So that would take your lambda would come out like this, and you would integrate from 0 to L x dx, and this integral is x squared over 2, and going from 0 to L, we would, let's go over to here, this is lambda over m. You would have here L squared over 2, you put the top one in, and then you would subtract the one with the lower limit like this, and that would get you L squared over 2, and then you have here L, you have here then lambda over m, and the lambda is your mass divided by your length, your density. So that means the masses cancel and one of the L's cancel, and you wind up with L over 2, which is our result for the center of mass. So you basically do the equation in one line is what you're doing there.